In this video, we'll look at how to recreate a drawing like this one using rigid links that are connected to each other, rotating at certain speeds. The rotational speed of each link is predefined. We just have to perform some mathematical moves to find the lengths of each link. Here, the rotating links are redrawing the Husky logo. Here are 6 links that have been disconnected. The top links are rotating clockwise, the bottom links counterclockwise. The middle links are moving twice as fast as the left links, and the right links are moving 3 times faster than the left links. Now, I'm going to put them all together so they're connected end to end. And I'll zoom in just so you can see it a little better. If we start moving them all again as they were, they start drawing this picture. Now all I had to do was calculate what lengths of the links do I need to make this picture of a heart. One of the things we'll see is that when you use more and more links, and here I have n being the number of links I'm using, the more you use, the more accurate your drawing will be when you're rotating all those links together. At 200, the Husky logo looks pretty good. All right, let's zoom in to where the drawing is actually happening, and all those links are moving in a pretty chaotic way. But these are just links that are increasing in rotational speed. They're all connected to each other, and I calculated the lengths that would draw this Husky logo. On the top right, you can see the zoomed out version. You can compare the zoomed in and zoomed out version to make sure the drawing is moving and wiggling in the same way. All right, the question is, if these links have predetermined rotational speeds, how do we calculate their lengths and initial orientation such that they draw what we want? Before we answer that question, we're going to review our previous topics first. Remember vectors, if you want to plot them, you can plot the first elements as the horizontal direction, the second element as the vertical direction. And here's the plotting of u and v. We can add these two vectors by adding the corresponding elements, right? 3 plus 0 is 3, and negative 2 plus 1 is negative 1. And you can plot that coordinate on the graph, 3, negative 1, and you can connect an arrow to the origin in that point, and that is the vector u plus v. A nice thing to remember is that vector u plus v is the diagonal of a trapezoid formed by v and u. Another thing we can do is scale the vector u by negative 0.5. And that just means scale each element in the vector u by negative 0.5, and you get the vector negative 1.51. And here's a plot of that. It is parallel to the vector u, but shrunk by a half, and it's in the opposite direction as the vector u because it was scaled by a negative number. We also define the dot product. So dot product of two vectors u and v is the scalar quantity denoted by u dot v, and all you do is multiply corresponding elements in the vectors and then add it all up. So here's an example, 3, 4 dotted with this 2, negative 5. We'll multiply corresponding elements and add them up, and you get the result of negative 14. Once you have the dot product defined, you can talk about the length of a vector, and we can also say norm or magnitude, which also means length. And if you have a vector with n elements, that means it lives in n-dimensional space, then the length of that vector, which is denoted by 2 bars around the vector on each side, that's equal to the square root of v dot v. Let's see why that's the case. We have this graph. This is the vector 3, 4. So you have 3 horizontally and 4 vertically. We know that the length of that vector is 5 because 3 squared plus 4 squared is 25, and then you take the square root to do the Pythagorean theorem. So that length is 5, that length of the hypotenuse of the right triangle. We'll check out the dot product of the vector with itself and then take the square root. You get 3 squared plus 4 squared and then the square root. So you get the same thing as what the Pythagorean theorem gives you. Once you know how to calculate length, you can find the distance between vectors. So distance between two vectors in the n-dimensional space is denoted by d parentheses u comma v. And that's just equal to the length of u minus v. So u minus v gives you a new vector. Right, by subtracting corresponding elements to get a new vector, then find the length of that new vector. Well, let's check it out. Here's a vector u and v, and the distance between u and v. I'll do the subtraction of corresponding elements. You get the vector 3, 4. Find the length of 3, 4 by doing the square root of the dot product of 3, 4 with itself, and you get 5, as we just did a second ago. And let's see why this works by plotting it. There's the vector u and v. The distance between u and v can be symbolized by that black arrow. We can form a parallelogram, and notice the black arrow is the diagonal of that parallelogram. Now if we plot negative v and reform that parallelogram, that diagonal now is the sum of u plus negative v, right? Because we saw that's how addition of vectors work. The new vector from the addition is the diagonal of the parallelogram formed by the two vectors that you're adding. So that diagonal vector is just u plus negative v, which is the same thing as u minus v. And so finding the length of u minus v is the same as finding the length between u and v. Once we know how to calculate the distance between vectors, we can talk about orthogonality of vectors, because if u and v are orthogonal, then the distance between u and v and u negative v are the same. Here's a picture of orthogonal and not orthogonal cases. In the orthogonal case, notice the distance between u and v is the same as the distance between u and negative v. That's not the case for the not orthogonal picture, right? The distance between u and v is different than the distance between u and negative v. Now, using that fact, we can derive a useful calculation to show when things are orthogonal. So, if those two distances are the same, then their distances squared are also the same. And now we can just write down what it means to be the squared distance between u and v. Remember, the distance between u and v is the length of u minus v, but now we're squaring it. And how do we calculate the length of something? We take the square root of the thing dotted with itself, but we don't need to write the square root because we're squaring it, so the square root and square cancel. And we have this dot product now that we can distribute. So u dot u plus v dot v minus 2u dot v. And notice that u dot u is just the length of u squared, because the length of u is the square root of u dot u. So it's really the square of u when you do u dot u. And likewise with v dot v, that's the length of v squared. We can do the exact same thing for finding the distance between u and negative v squared. Right? Write that as the length of u minus negative v squared. Rewrite what the length of that means being squared, so the dot product of the thing with itself. You don't have to do the square root because it's being squared. Distribute those dot products, and we get a very similar result. The length of u squared plus the length of v squared plus 2 times u dot v. Now the only way these two results can be the same, right, because these two distances squared need to be the same when we have the orthogonal situation. The only way that can be true is that if u dot v is 0. So if u and v are orthogonal, then u dot v is equal to 0. That's the only way for these square distances to be equal, because the length of u squared and the length of v squared are always positive. So the only way for those two distances squared to be equivalent is that if u dot v is 0. If u dot v was not 0, then those two squared distances would be different, because you have minus 2 times that dot product for one calculation and plus 2 times that dot product for the other calculation, and they'd be different. Now, orthogonality is important because it has this idea of closeness associated with it. All right, so given v, w1, and w2, where w1 and w2 are orthogonal, so here's a graph in 3 dimensions, and we're going to wonder if we're restricted to working just in the plane produced by w1, w2, that is all linear combinations of w1, w2, all scaling and adding up of w1, w2 would give you that plane. If we have to stay in that plane, what's the closest spot to v if we have to stay in that plane? So another way to say this is, what linear combination of w1, w2, scaling and adding up of those two vectors, w1, w2, would get us closest to v? Well, we'd be closest when the vector connecting v and that linear combination is orthogonal to that plane. And we're going to call that perpendicular vector, that orthogonal vector, z. So our goal is to find c1w1 plus c2w2. Notice that linear combination plus z gives us the vector v. Right? So if you add up those 3 vectors, you get v. And we can calculate the values of c1 and c2 by first noticing the fact that z dotted with w1 is 0. Right? Z and w1 are orthogonal. So you can replace z with what it's equal to. Right? Rearrange the bottom left equation that's noted there. Solve for z and plug it in. And so that's v minus c1 w1 minus c2 w2. Distribute that dot product through. And notice that third dot product is 0 because w2 and w1 are orthogonal. And when things are orthogonal, the dot product is 0. And so we can solve for our c1 to be v dot w1 divided by w1 dotted with w1. So it's a ratio of dot products. We can also solve for c2 by also noting z dotted with w2 is 0 because they're orthogonal. Do the same thing. Plug in z, distribute the dot product. Notice that w1 dot w2 is 0. And so you can solve for c2 as the ratio of those dot products. And these two ratio of dot products are really important. You definitely want to remember these and maybe stop the video and study these calculations, because these ratio of dot products is what gets us closest to a vector that does not live in the plane that we're restricted to, as long as w1, w2 producing that plane are orthogonal. And you can extend this to as many dimensions as you'd like. Now we're going to generalize the idea of a dot product so that we can work with more than just vectors in the n-dimensional space. So the dot product for two vectors in R2, is two-dimensional space, was defined to be multiply the corresponding elements and add them up. So u1 v1 plus u2 v2. And we use this new notation with the angled brackets u comma v to denote what's called the inner product. So a dot product is just a specific instance of a inner product. And the inner product is going to be this more general concept. So what we would like to do is do the same exact thing for functions. So for functions f and g on an interval a to b, let the inner product be defined as, well, multiply corresponding elements in the functions. So like the corresponding y coordinates for certain x coordinates. So multiply them all together and add them all up. But this would be a problem because functions on a closed interval a to b has an infinite number of values. So you'd be multiplying an infinite number of elements, then adding up an infinite amount of terms, and that would be problematic. But it'll be helpful to write this in summation notation. Right? The summation of f of x of I times g of x of I from I equals 1 to infinity. Now this should look somewhat familiar. Now this calculation doesn't work, but what we could do is realize this looks like an integral. So for functions f and g on the closed interval a to b, let's define the inner product instead to be the integral of f times g dx from a to b. Right? Because the integral, the area under curves, was developed from adding up a finite number of things, but letting the number of things you add go to infinity. So it's a very similar thing here, but now we're finding the area under f times g instead of adding up an infinite number of terms f times g. Now the concepts we developed with dot products is the length of a vector, the distance between two vectors, and orthogonality. Those can be generalized to inner products, right? Especially this inner product defined with the integral. So here they are, and notice they resemble the same properties and concepts of a dot product. The length of a function f is just the square root of the inner product of f with itself, but the inner product is an integral. Right? So we have the square root of the integral of f times itself from a to b. Same thing with the distance between f and g. It's just like the dot product version. And orthogonality, well, the way to check the orthogonality is take the integral from a to b and multiply f and g together. And find that integral. And if it's 0, then the two functions are orthogonal. A nice one to intuitively check is the distance between f and g. Right? The only way for the distance between f and g to be 0 is if f and g are the same. And check out the integral. You'd be doing f minus g, where f and g are the same. So that'd be 0. The integral of 0 squared is 0, because the area under the 0 function is 0. So that kind of intuitively matches our understanding of what a distance between two functions should be. Right? If f and g are the same, then the distance is 0. The area calculated by the integral would be 0. All right, now we're ready for what's called Fourier approximations. So if you have this set of functions where the first function is y is equal to 1, so it's a constant function, and cosine of x, cosine of 2x, incrementing all the way up to cosine of nx, and then sine of x, sine of 2x, incrementing all the way up to sine of nx. So there's n cosine functions and n sine functions and one constant function. So there's 2n plus 1 functions in total in the set. And Fourier realized that the integral of f times g dx from 0 to 2 pi is equal to 0 when f is not equal to g and f and g are in the set S. So for example, if f was cosine of x and g was sine of 3x, if you computed that integral, you'd see it 0. And that's true for any two distinct functions in this set. You do that integral, and it's 0. And what this means is that the 2n plus 1 functions in the set S are orthogonal in this inner product space of all continuous functions on the closed interval from 0 to 2 pi. This is super convenient. Before, if we were given some set of functions, by chance they're definitely not going to be orthogonal, so we'd have to use what was called the Gram-Schmidt process to produce orthogonal functions that would span the same space as the original functions. But here we go, we just have cosine incrementing in frequency and sine incrementing in frequency, and they're all orthogonal. So we can approximate a function f like this with our functions in our set S. Notice all these ratios in front of the cosine and sine terms and the constant function 1. Those are ratio of inner products, just like we did before with vectors. We had the C1 and the C2 as the ratio of dot products. It'd be great to compare that formula with vectors with this formula here with the functions. It has the same exact structure. We're just using this generalized idea of a inner product to find the closest you can get using sine and cosine and the constant function 1, closest you can get to the function f. So this is the main takeaway from Fourier approximations. We can simplify this formula by calculating all the denominators in those ratios. So the first denominator is the inner product between 1 and 1. So that's just the integral of 1 from 0 to 2 pi. And that's equal to 2 pi. You can do that one by hand. And all of the other denominators, so the inner product between cosine of itself and cosine of 2x in itself, sine of x in itself and sine of 2x in itself, and so on, all of those are equal to pi. You can calculate those integrals by hand or use a calculator and verify that those integrals are pi. So all of the denominators are calculated. All you really have to do is calculate the numerators, and you can't calculate them ahead of time because we don't know what our function f is. Once we do know what f is, then we can calculate all those numerators, and that'd be finding the coefficients that go in front of all of our functions. Now the Fourier approximation can be rewritten in a really nice way as this linear combination where those coefficients are those ratio of inner products. And the way you calculate those coefficients, which are called Fourier coefficients, are by these integrals. And notice we already calculated denominators, right? That was 2 pi and the pi. So that's the 1 over 2 pi and the 1 over pi and the 1 over pi that you see for a naught, aj, and bj. And so really you're just calculating those numerators. So this would be a great spot to stop and look at how we derived all of this. And this is what we're going to use to do in a Fourier approximation to find the best way, how you can get closest to a function f just by using cosine and sine terms and a constant function. All right, let's look at a second order example. So find the second order approximation of the function x from 0 to 2 pi. Now second order means we're going to let n equal to 2. So we have to calculate all these integrals, right? So these 5 integrals here. And you can do that by hand or use a calculator. Right, so I calculated these and get pi for a0. We get 0 for a1. We get 0 for a2. Get negative 2 for b1. We get negative 1 for b2. So our approximation to the function x on the interval from 0 to 2 pi is pi minus 2 sine of x minus sine of 2x. Right, we calculate the coefficients in front of the constant function 1 and the cosine of x, cosine of 2x, sine of x, and sine of 2x, but you don't see the cosine terms because the coefficients were 0. And here's a picture of our approximation to the function x from 0 to 2 pi. Now you might be wondering, how would we approximate functions on a different interval? Maybe we don't want to do 0 to 2 pi. Well, we'd have to slightly adjust our sine and cosine functions to have different frequencies so that they're still orthogonal on the interval. We're not going to cover that in this video, but you can look into that if you'd like. All right, now we'll look at an nth order example. So not any particular n, like n equals 2 or n equals 4, but for any n. So let's find the nth order approximation to that same function x from 0 to 2 pi. We already calculated a 0 that happened to be pi. Now let's calculate all the other 8 terms, right? All the ones in front of cosine. So we can just put a j in there instead of like a 1 and a 2 and a 3. Let's just do it for any integer j. And I used Symbolab, and it gave me 2 times sine of 2 pi j, all divided by j. But notice, j is always going to be an integer, right? 1, 2, 3, 4, 5, 6. And sine of 2 pi times any integer is always 0. So those terms are always 0. And we can do the same thing for all the b terms, right? Just do it for a general j that represents an integer. And Symbolab gave me this fraction. And the same thing, right? J is equal to 1, 2, 3, 4, all the way up to n. So it's always a positive integer. And sine of 2 pi times the integer is always 0. So that term goes to 0. And the cosine of 2 pi times the integer is always going to be 1. So you can rewrite this as negative 2 over j, right? Because cosine is 1. You have a pi divided by pi, so the pi disappears. And the 2j over j squared is just 2 over j. You still have that minus sign, so negative 2 over j. So this means b1 is equal to negative 2 over 1, b2 is equal to negative 2 over 2, b3 is equal to negative 2 over 3. So you can write the Fourier approximation like this. Pi minus 2 over 1 sine of x minus 2 over 2 sine of 2x, all the way to minus 2 divided by n sine of nx. And if you prefer summation notation, you can write it like this. All right, I typed our formula into Desmos to see what it looks like for a different n. So n equals 1, 2, 3, 4, all the way up to 10. It looks pretty good at 10. You can change it to go to a bigger n, but I'll leave it there. You can see that it gets to be a better and better approximation. Let's look at another nth order example, this time with the step function, where the function is a value of 1 from 0 to pi, and after pi is a value of 0, so all the way up to 2 pi. So the first term, that constant term, can be calculated by just integrating the function from 0 to 2 pi, and scaling it by 1 over 2 pi. And that happens to be 1/2. You can check that by hand. The other ones you could do with the calculator, again, instead of doing A1, A2, A3, and so on, just do AJ, and use Symbolab. That's what I used. And instead of doing cosine of x, 2x, 3x, 4x, just put a j in there. Let j be any integer. And what you end up getting is 0 for all of those. Same thing with bj. Just put a j in there for a positive integer. And Symbolab would give you this result for the integral. And notice when j is even, you'd have 1 minus 1. So the numerator would be 0. So the whole thing would be 0. But when j is odd, you'd get 2 in the numerator. And so you have 2 over pi j. So 2 over pi j would be the terms in front of the sign terms only when j is odd. Right? When j is even, you'd have 0. So that's for odd j. You can write your Fourier approximation like this. Notice that you only have the odd terms, so 1, 3, 5, and so on, all the way up to your n. And you can rewrite it as summation notation like that. And here is a Desmos graph again, with the red function being our step function and our blue function being our approximation to that step function. We'll let n go to 2, then to 3 and 4. keep getting bigger. This time I'm going to go all the way to n is equal to 100. That's what it looks like at n is equal to 100. All right, let's look at one more example. Find the nth order approximation of f of x is equal to x squared from 0 to 2 pi. So the term a0, so that constant function, this coefficient, would be 1 over 2 pi times the integral of x squared from 0 to 2 pi. So that's 4 pi squared over 3. Right, that would be one you could do by hand or using a calculator. And the other ones, you want to use a calculator. Right, so same thing here as usual. Instead of doing a1, a2, a3, and so on, just do aj, where j is a positive integer. And use a calculator. Instead of cosine of 1x, 2x, 3x, just put j in there. And you get 4 over j squared. And likewise with bj, right, the terms, the coefficients in front of sine, you get negative 4 pi over j. So you can write the final formula for the approximation in summation notation like that. All right, and here's a plot of our approximation at n equals to 1. And I'll go all the way up to 100 again. You can see it gets better and better. Here's n is equal to 100. All right, we finished all the math that you need for the homework. Now we'll look at the math behind the rotating links that we started the video with. So let R of n be this matrix of cosine and sine functions. And if you plugged in a number n and t into those functions, that would be a 2 by 2 matrix that would rotate vectors about the origin by an angle nt. So that's called a rotation matrix. We'll look at integrating matrices of functions. And what we mean by integrating a matrix is integrate each term in that matrix, as shown here. Now let the inner product between r of n and r of m be this integral from 0 to 2 pi of r of n multiplied by r of negative m. So you have a multiplication of two matrices of functions here. Why is it negative m? We'll talk about that in a moment. But now consider this set of matrices of functions, r of 0, r of 1, r of negative 1, r of 2, r of negative 2, all the way to r of n and r of negative n. All right, we finished all of the math that you need for the homework. Now we'll look at the math behind the rotating links that we started the video with. So let R of n be this matrix of cosine and sine functions. And if you plugged in a number n and t into those functions, that would be a 2 by 2 matrix that would rotate vectors about the origin by an angle nt. So that's called a rotation matrix. We'll look at integrating matrices of functions. And what we mean by integrating a matrix is integrate each term in that matrix, as shown here. Now let the inner product between r of n and r of m be this integral from 0 to 2 pi of r of n multiplied by r of negative m. So you have a multiplication of two matrices of functions here. Why is it negative m? We'll talk about that in a moment. But now consider this set of matrices of functions, r of 0, r of 1, r of negative 1, r of 2, r of negative 2, all the way to r of n and r of negative n. And the neat thing is that the integral of r of m times r of n is the 0 matrix when you integrate from 0 to 2 pi. Only when m is not equal to n.